And so why are these, not really talked about very often? A lot of, these first three categories are talked about a lot, but why are shape operators not discussed? Well, in the dense world, with an array that looks like this, where you store the dimension, the shape, and a flat array of float values, a simple reshape looks just like this. You just return, a new array with a new shape. This is an O of 1 time metadata update. And in fact, most of the shape operators are O of 1 metadata updates. However, in the sparse world, this is not the case. So consider a common sparse array format, the coordinate list. I've shaded non-zero values in gray here. The coordinate list also stores the dimensionality, also stores the shape, but it also stores the number of non-zeros and a coordinate for each of those number of non-zeros, and then a value for each of those non-zeros. So it looks a little bit like this. Reshape for the coordinate list array is far more complicated than just an O of 1 time metadata update. So first, we need to allocate a new list for the coordinates, the updated coordinates. And then we need to iterate over each coordinate, remapping it into the new space, the new 2D space. So this is an O of the number of non-zeros size computation. It's no longer just an O of 1 metadata update because coordinate list arrays do not store O of 1 metadata. They store O of the number of non-zeros metadata. But there's so you might be looking at this and go, AJ, that's 4 lines of code. Like, why do you have a whole paper on this? Why does this matter? Coordinate list array is not the only sparse array data type. There are a lot of sparse array data types. There are compressed sparse columns, compressed sparse rows, and hash formats, diagonal lists, and like this goes on. There's always more papers on new sparse data structure formats. And so for every operation that I talked about beforehand, you need to implement any operation that you care about for all of these data structures for like a good sparse array programming system. And so we're not the first, like by far, to try to tackle this problem. So the Taco compiler published in OOPSLA a few years ago, figured out how to map tensor algebra to a large number of these data structures. Follow-on work at OOPSLA a few years ago, figured out how to map arbitrary semirings onto these data structures. And if you stick around for the next talk, you'll see how to map convolutions onto these sparse data structures. But for now, I'll be talking about shape operators. And perhaps most importantly, shape operators fused with other operations on this list, fused with compute operators. Also, if you're curious, we call this system burrito because it extends taco, and a burrito is what you get when you reshape a taco, which I'm very proud of. So getting back to this, what is the real benefit that these systems offer? Well, when you have n operations, k operations and n data structures, a naive implementation of just implement all of the operations on all of the data structures requires a quadratic amount of work. These compilers each implement some sort of intermediate representation that linearizes this term into developer work per each data structure and per each operation. But this is not the only solution. You don't have to go through a compiler to get this sort of like linearized work. So here's what the state-of-the-art libraries do, like scipy.sparse and pydata.sparse. They define n conversion types to a common sparse array format. In this case, the COO matrix type that I showed you before. Then they define a shape operator for the COO matrix. They define each shape operator for the COO matrix. And then they have n conversions from COO back to whatever type that you want. So if we want to, for example, implement a reshape of a CSR matrix and produce a CSR matrix, we first convert the input CSR to COO, perform the reshape, and then convert the output back to CSR. So this is great. This means that we've done O of k plus n work, right? Like this is great for developer productivity. But this is not good for performance. Each one of these kernels is a memory allocation and an iteration over the entire sparse data structure. And this is somewhat problematic, and our results show that this is actually like really bad for performance. So this is just a sample of the results in the paper, but on 3 sparse shape operators, we show an order of magnitude speed up over scipy. These plots are log scale, blue is us, time is on the x-axis, and the number of non-zeros is on the y-axis. And so you can see that we're an order of magnitude faster than scipy, and we're close to 3 orders of magnitude faster than pydata, which is pretty bad. And the only benefit to our system here is that we generated code specialized to the data structure and removed these expensive memory allocations. I just want to note, I don't show this in the talk, but for kernels where these systems don't do expensive memory allocations, we achieve essentially parity, plus or minus a little bit. But there are more benefits than just data structure specialization. And the other benefit is operator fusion. So consider stacking 2 matrices, B and C, and doing a matrix vector multiplication on D. That looks visually something like this. Where to compute one element of the output, we iterate over all of the row of B and C and the entire column of D. And we just keep stepping forward. But consider the case that D is sparse. We only have 2 elements now in the beginning chunk. To compute the first element of A, we only need to iterate over B, right? We can completely skip iterating over C. And that's the case for all of the elements of A. If we do not perform fusion, and we first compute a temporary that is equal to the concatenation of B and C, and then multiply the temporary by D, we have to construct this temporary that iterates over all of B and C. And that can be really expensive. So we also show in the paper some performance benefits of fusion. These performance benefits are a little bit more modest, but they're still good, and together with data structure specialization can become even more powerful. Once again, burrito is in the blue, red is scipy, and yellow is actually burrito code that's unfused. We wanted to show sort of just the benefit of fusion, not the benefit of our code generation over other systems. So hopefully, these results are a little bit motivating in terms of like a compiler is good for this problem. But I want to emphasize one further point. Fuse code is super messy and extremely complex. And I don't expect you to read this. I, in fact, made this so small that you can't read this. But this is just one of those kernels from beforehand. And there is a ton of complex control flow. It's very hard to generate this, to handwrite this code. And in fact, like handwriting a lot of this code sometimes would get it wrong. So it would be great if if a compiler can generate this code with some reasonable correctness guarantees. So the way that we do that is via a compiler that extends the Taco compiler. So we first extend Taco's input language with shape operators. Then we extend Taco's intermediate representation for representing iteration spaces with some operators that are specific to shape operators. And then we have a novel IR and some optimizations and a code generation technique. And in gray is illustrating our contributions into the Taco compiler. But today, I don't have time to talk about all of this, so I'm really just going to focus on code generation and the new IR for representing sparse iteration spaces. So please see the paper for more details. To start, though, I'll talk about what Taco, before this paper, used to represent iteration spaces. So for a simple vector addition or vector element-wise multiplication, Taco represents these iteration spaces as intersections and unions. If you're adding 2 sparse vectors, there is a non-zero coordinate in the output anytime either of the first 2, the upper end vectors, have a non-zero coordinate. If you're element-wise multiplying, there's a non-zero in the output only when both inputs have a non-zero coordinate at that location. So we spent a lot of time thinking about how do shape operators fundamentally transform these iteration spaces over coordinates. And this is what we came up with. So consider a 2D matrix on the left and a flattened iteration over that 2D matrix on the right. If we label the iteration space of the rows by I and the iteration space of the columns by J, the iteration space of the flattened or reshaped matrix, it looks something like a Cartesian product. And in fact, we define this product operator to be a strided offset formula applied to the Cartesian product of I and J. And this accurately represents a non-zero coordinate in the flattened vector anytime there's a non-zero coordinate in the original matrix. And so we actually define operators, set operators like this for coordinate spaces for all of the sort of primitive shape operators that can be used as building blocks for more complicated shape operators. So we have the product operator. For concatenation, this is a disjoint union. For splitting, which is the inverse to the product operator, so it's not flattening, it's unflattening, this looks like a set projection. And slicing is a simple filter on the coordinate space. And so I just want to emphasize this IR is used to represent iteration spaces over, so like the iteration space of a loop. So in one of the fused examples that we had before, if you want to flatten a 2D matrix and element-wise multiply that by a compressed vector, which looks like this visually, we generate, or we label the rows by I, the columns by J, and then the iteration space of the vector by K. The for loop over this computation looks like this, where we iterate over all K in the product intersected with K, and then perform a multiplication. So this code is a very simple and non-sparse way of thinking about the iteration space. Like nothing here is sparse so far. This is just an intermediate representation for thinking about iteration itself with shape operators. But we still unfold this into a massive amount of code with a lot of complex control flow. So I want to talk a little bit about the intuition behind how we do that, how this one for loop unfolds into the code that you see here. And we do it via a rather old idea, the iterator model, which comes from, I think, from the databases community, or at least I've traced it back as far as the 90s in the databases community. But you can really think about this as the iterator model in most programming languages that you can think of, like C++ and other programming languages, where you initialize an iterator, you have a valid check to see if the iterator can keep going. And then there are a couple of other extensions to the iterator model that I won't talk about today, but you should read the paper for more details, like locate and evaluate. And then you want to get the next value of the iterator. So let's walk through how to do this on the product iterator. If I want to iterate over a product B, how do I initialize this? Well, I first initialize A, and then I initialize B. And then if B is initially empty, then I iterate over each of the elements of A, resetting B until B is non-empty, or A is completely empty. And so this basically finds the first non-zero element of A product B. Now, how do I know whether or not to keep going? Well, I keep going if A and B are both valid. And how do I get the next non-zero coordinate? Well, it's very similar to how I initialized. I step B forward to get the next value of B, and then if that has stepped B off the edge of being valid, I keep going until I find the next time that B is non-empty. With that, I'm getting signals that I'm running out of time, so I want to close with some final thoughts. I really want you to take away from this talk that shape operators are really the typecasts of array programming. A nice way to linearize this quadratic problem is via an IR for iteration, and that shape operators fundamentally transform iteration spaces, but they're not computing on iteration spaces. And that the iterator model is a really nice way to compile this sort of complex irregular computation. So I'm happy to take questions.
Very interesting work. I was wondering, so you mentioned the database community. So for the problem of fusion, actually, they have two models. So one is the iterator model, one is the so-called push model. So, and it is kind of well known there that the iterator model causes the control flow of the generated code to be very complicated. So did you face with that issue during your code generation, or it was okay?
I did not. I mean, the control flow generated is rather complex. It's not code that I would ideally like to write by hand. Each of those, initialize A and initialize B unfolds to actually initializing a sparse iterator, and that code gets really complex. But the iterator model itself is like so nice to reason about that like it's very easy to check correctness just based on like assuming A is correctly initialized, like the initialization of A product B. Like correctness is very easy to check without like knowing how A and B unfold, like initialize A and B unfold. So I didn't like the generated code is kind of messy. It might be better if we followed the push model, but it's just not how we ended up implementing it. So.
Okay, thank you.
Thank you.
Hey, thanks for the talk. So you mentioned earlier that there are a lot of different sparse data formats, and how did you choose which ones will be integrated into the IR? As new ones emerge, how are you going to integrate those? That type of stuff. Yeah,
so that's an excellent question. So we actually did not change anything about how Taco represents sparse data structures. So basically for each individual sparse data structure, Taco represents them as if you have like an n-dimensional matrix, you say that like, oh, this dimension is dense, this is compressed, this is dense, this is compressed, etc. As long as each of those like level formats are defined via the iterator model, our code generation algorithm can generate code for them. So it works for anything that Taco works for. So yeah, yeah, no problem.
So I had a bit of a question. So it seems like one of the core foundations for this, and maybe some of the other operations within Taco, is based primarily on the iteration of it. So there's two things I'm wondering, coming from the performance angle, is there any kind of consideration that could be applied to the same model for when not all of the same memory has the same access times? You have something like non-uniform access times to a locality element basically, where some regions of the array are faster to access than others, and similarly, is there any kind of consideration that could be incorporated in for some form of parallel operation on the arrays, where you might have like say multiple threads trying to work together? Yeah.
So let me answer the parallel question first because that's easier. All of our generated code is like embarrassingly non-parallel. This is really complex control flow that is like not easy to parallelize. Nothing that we compare against does anything parallel either, besides some minor like vectorization, but no like parallel loops or anything like that. I think that it's very non-trivial to parallelize sparse code in general. I think a lot of papers figure out how to parallelize a single sparse operator on a single like sparse data structure, and there still needs to be a lot more work in figuring out how to parallelize arbitrary sparse computations on arbitrary data structures. To answer your memory models question, I have placed no consideration on that. One of my very, very excellent lab mates, though, Olivia Xu, who conveniently is on the academic job market, by the way, does think about this and is working on models for analyzing programs via like memory access patterns and stuff, like memory latency times and stuff like that. So you should look at Olivia's work, and yeah.
All right, so let's thank AJ again.